physics, there are many, many units, and you've come across a lot of these already. Think of things like volts, or coulombs, or amps, or joules, meters, seconds, degrees Celsius, etc. In fact, though, when it comes down to it, there are actually only 7 fundamental units, and all the other units that we use in physics are combinations of these units. Now, these fundamental units are as follows. We've got the meter, and the meter is the unit for length or for distance. We've got the kilogram, and the kilogram is the unit for mass. We've got the second. The second is the unit for time. We've got the amp, and the amp is the unit for electric current. Notice it's capital A for amp. We've got the Kelvin, and Kelvin is the unit for temperature, and that's capital K there. Notice we don't put a degree sign before the K for Kelvin as well. We've also got the mole, which is the measure of the amount of something, and the symbol for there is just MOL. And we've got something called the candela. Now, this is a unit for luminous intensity, and at IB level we tend not to use this one. A lot of students are surprised when they first look at this. They're surprised that some of the familiar units that they're used to from GCSE level don't appear here. For example, one such unit, the Newton. Now, the Newton, just by its name, sounds like it should be very fundamental to physics, but in fact the Newton is a combination of a couple of these fundamental units. So let's see what a Newton really is. Well, Newton is a unit for force, and one equation for force is that force equals mass times acceleration. Well, shall we just consider the units for this kind of equation? Force is measured in newtons. Over here we've got mass, which is measured in kilograms, and we've got acceleration, which is measured in meters per second squared. Let's write that out again, but a bit more like we should write it at IB. It would be kg multiplied by ms to the minus 2. Then just to make it even more simple, kg ms to the minus 2. Well, what we've shown here is that by using the equation force equals mass times acceleration, we can show that in fact 1 Newton is equivalent to a kilogram multiplied by a meter multiplied by a second to the power of minus 2. So a Newton is not fundamental. It's a combination of kilograms, meters, and seconds arranged in a particular way. Another unit that people are surprised to not find on the list of fundamental units is the Joule. The Joule is the unit for energy, and energy, after all, is quite fundamental to physics. So what exactly is a Joule? Well, we know that Joule is the unit for energy. We also know that work done is energy. So let's write out the equation for work done. Work done equals force times distance. Now, work done is a unit for energy, is another word for energy, and we know that that's measured in joules, so we can put joules over this side. Force is measured in newtons. Distance is measured in meters. So interestingly enough, a joule is in fact the same as a newton meter, newtons times meters. But newtons themselves are not fundamental units, as we've just seen. A newton is in fact a kilogram times a meter multiplied by a second to the minus 2. So actually a joule, by doing newtons times meters, is kilograms meters per second to the minus 2 times by meters, which gives us kg m squared s to the minus 2. So a joule is not a fundamental unit. In fact, a joule is a combination of 3 fundamental units: kilograms, meters, and seconds. We get kilograms multiplied by meters squared, multiplied by seconds to the power of minus 2. And that's what a joule is, expressed as fundamental units. Fundamental units can be quite useful because what they can do is they can help determine whether an equation is correct or whether it's incorrect. Let's think of an example. Let's say that you were looking at the equation for kinetic energy. Now we know that equation from GCSE is a half mv squared. But what if somebody came up to you and said they'd proved that actually the equation in fact was a half mv cubed? Now of course we know which one's the right one, but fundamental units are a really good way of testing whether equations are correct or not. We know that energy has to be measured in joules, and what we need to do now is check whether the fundamental units in this version of the equation will give us joules, or whether the fundamental units in this version of the equation will give us joules. So let's work it out. We take each term in order. The half has no units, so we can ignore it. The mass is in kilograms. We know that speed or velocity is in meters per second, so we do ms to the minus 1 there, and the whole thing is squared. So that looks like kg m squared s to the minus 2. Now let's say if we wanted to do the same thing for this equation. We know it's joules over this side. The half has no units, so we can ignore it. The mass is kg. The speed there is meters per second, and this time it is going to be cubed. So we're left with kg m to the power of 3 s to the power of minus 3. Now you can see from what I wrote up here at the top that kilograms meters squared times seconds to the minus 2 is in fact the unit for joules. Therefore this equation must be wrong. This equation could be correct. Notice I didn't say it must be correct. I'm saying it could be correct, because this half here may or may not be correct. The units can't tell us that. It's just a number. However, it tells us whether our equation is broadly in the right area or not. Now we're going to try something a little more sophisticated in terms of how we use fundamental units. Up here I've written that the Newton is a kilogram times a meter times a second to the minus 2. Here is an equation that you'll come across when you study gravity. It's about the force between two masses, and it tells us that the force between two masses due to gravity is equal to this number, capital G, which is a constant, which you'll find in your data booklet, multiplied by the mass of one of the objects, multiplied by the mass of the other object, divided by the square of the distance between the two objects. Now, our task that we're going to set ourselves is to see if we can express this value of G in terms of fundamental units. So the first thing we're going to do is we're going to rearrange the equation to see what G is. Now G will be equal to F multiplied by R squared, and we will divide that by M1 times M2. Then what we'll do is we will now express this in terms of units. Well, F is a force, so that's measured in newtons. R is a distance, so that's going to be measured in meters squared. And here on the bottom we've got kilograms multiplied by kilograms, so that's going to be kilograms squared. Now if you look at G in your data booklet, it will give you the units as newtons times meters squared times kilogram to the minus 2. But this is not quite yet into fundamental units. Remember, the Newton is not fundamental. The Newton is in fact kg m s to the minus 2. So when we've got newtons multiplied by meters squared, we've actually got kg ms to the minus 2 multiplied by meters squared. This whole thing is then over kilograms squared. Well, let's see if we can tidy this up a little bit. This kilogram here can cancel with this number 2 there, leaving that to be just a 1, so kilograms by itself. And let's see what we've got. We've got meters multiplied by meters squared, so we've got meters cubed. We've got seconds to the minus 2, and the whole thing is divided by kilograms. Now, we don't normally leave it with the dividing sign like that. We would write it like this: meters cubed, s to the minus 2, kilograms to the minus 1. So the fundamental units for this constant g are in fact meters cubed times seconds to the minus 2 times kilograms to the minus 1.